Okay guys, in this video we're going to be talking about the effusion and diffusion of gases. So we'll define those processes, and then we're going to look at Graham's law for calculating the rates of effusion and times it takes for a gas to effuse. So diffusion is the process where one gas spreads through another gas. And then effusion is the process where one gas goes through a small pinhole through its container. So in this picture, you've got two gases, and one gas is concentrated over on one side of the container. Gradually over time, the gases will completely mix and be a homogeneous solution all throughout. In the case of effusion, we're looking at how gas molecules go through a small hole and the rate at which they go through that hole. It turns out that the rate of both processes, so the rate at which a gas spreads out and the rate at which a gas effuses through a pinhole, obey the same law. They obey Graham's law. So assuming that the containers that we're talking about have some value of pressure and temperature, the rate of effusion, which is defined as the amount of gas that passes through the pinhole in a given amount of time, that rate is proportional to 1 over the square root of the molar mass of the gas. Okay, so this is Graham's law for diffusion and effusion. The rate of effusion is proportional to the square root of 1 over the molar mass of the gas. So the heavier the molar mass, the slower the rate. The lighter the molar mass, the faster the rate. You can also rearrange this equation and solve for the time that it takes for a gas to diffuse or effuse through a pinhole. So rearranging the equation, you can write the time that it takes as the amount of gas divided by the rate. And what you'll find is that is proportional to the square root of the molar mass. So the smaller the gas, the smaller the molar mass of the gas, the shorter amount of time that it takes for the gas to effuse. Okay, so if you had helium effusing through this pinhole, it wouldn't take very long. But if you had something heavy like xenon with a large molar mass, that means it would take more time. So the xenon would proceed more slowly with a slower rate and taking a longer time. We will be using these equations here using a ratio trick where we compare the rate of one gas to another gas. So this would be at what rate does gas 1 effuse compared to the rate at which gas 2 effuses. And it's going to involve the square root of the ratios of the molar masses. And so let's look at some problems involving gas effusion and gas diffusion. So here we're being asked to calculate the ratio of the rate of effusion of hydrogen gas to the rate of effusion of oxygen gas. So the rate of effusion of hydrogen, according to Graham's law, is proportional to the square root of 1 over the molar mass of hydrogen. And you have the same thing for the oxygen gas. Now they're asking us to take the ratio of these two rates. So we would take rate H2 divided by rate O2, and then that's going to be the square root of 1 over the molar mass of hydrogen divided by the square root 1 over the molar mass of the O2. We can simplify this and make it like so. And then we can actually calculate the number. We would have 32 over basically 2. Okay, so this would give us the square root. This is the square root of 16. And so we're going to get a ratio of about 4 for this problem. Here's one that's a little bit more quantitative. At a particular pressure and temperature, nitrogen gas effuses at a rate of 79 milliliters per second So that's the rate. Using the same apparatus and the same pressure, at what rate will sulfur dioxide effuse? Okay, so we're going to need the molar mass of N2, which is 28 grams per mole, and we're going to need the molar mass of SO2, which is 64, roughly. Okay, so here's how we use this. So the rate of N2 is known to us, so we know that number. And then the rate of SO2 is what we want to calculate. So we want to calculate that number. And the rate of N2 is 1 over the square root. It's proportional to 1 over the square root of the molar mass of N2. And then the rate of SO2 is proportional to 1 over the square root of the molar mass of SO2. And again, we can simplify that like so. Now, what we want to do is solve for that number in terms of all the other numbers. So the rate at which SO2 effuses is going to be equal to the rate at which N2 effuses times the square root of the molar mass of N2 divided by the molar mass of SO2. So we'll take the 79 milliliters per second, and we'll take that times the square root of 28 over 64, and that's going to give us the rate at which the SO2 effuses. So just running these numbers through the calculator, I'm getting 52.3, so we'll just say it's 52. It's going to be milliliters per second. So we find that, as expected, the SO2 has a larger molar mass, and so it is going to have a slower rate compared to the N2, which is a faster rate. This is identical to the problem that we did before. The only difference is they want us to replace the gases hydrogen and oxygen with CO2 and SO2. So I'll leave this as an exercise for you guys to try. We're going to go ahead and take a look at this problem. So here, this problem is slightly different than the one that we worked before. So here they're telling us it takes 3.52 seconds for 10 milliliters of helium to effuse through a hole in a container. How long would it take for the same amount of oxygen to effuse under the same conditions? So here we're not dealing directly with the rates, we're dealing with the time. And so the time that it takes for helium to effuse is not proportional to 1 over the square root of the molar mass of helium. It's proportional to the square root of the molar mass of helium itself. Okay, so not the reciprocal, but the square root of the molar mass itself. And the same thing is true for the O2. So what we'll do is we'll take a ratio of the two equations. And then what we'll do is we'll solve for the time it takes for O2 to effuse. So it took 3.52 seconds for the helium. And then we'll do the square root of 32 for oxygen divided by 4 for the helium. And as expected, because the oxygen has a larger molar mass, it's going to effuse more slowly, and it's going to take 9.96 seconds for 10 milliliters of oxygen to effuse through the pinhole in the container. It's the same time-based problem, but they're asking you to find the molar mass. And so they're saying if it takes 4.67 times as long for a particular gas to effuse as it takes for hydrogen to effuse under the same conditions, what is the molar mass? And so what they're saying is that the time that it takes for this unknown gas to effuse relative to the time that it takes for hydrogen gas to effuse is equal to 4.67. And that's also going to be equal to the square root of the molar mass of this gas divided by the molar mass of the hydrogen. So we can now solve for the molar mass of the gas. It's going to be 4.67 squared times the molar mass of hydrogen. And so I'm getting 44.0 grams per mole for that molar mass. And so here we've actually used the effusion process to estimate the molar mass of an unknown gas, which is kind of a neat application of this. Well, I'm going to go ahead and stop this video here, and then we'll start with the kinetic molecular theory of gases in the next one.